Hello everyone, welcome to the Medical Electronics Project video. My name is Dylan from PE05 and today I'll be explaining the circuit. I'll be explaining the individual stages, with stage 1 being the pre-amplifier stage, stage 2 closed loop inverting amplifier, stage 3 active filter stage, and stage 4 audio amplifier stage. So what do amplifiers do? Amplifiers are a form of circuit to provide amplification to increase the strength of a signal. So this is the overview of my circuit, which consists of stage 1 to stage 4. For stage 1, the pre-amplifier stage, the input would be at TP1 and output at TP2. And the TL072 IC is used, which is a dual low noise JFET operational amplifier. This operational amplifier has a very high input impedance along with a low noise output, which makes it an ideal op-amp. The JFET stands for Junction Gate Field Effect Transistor, and this JFET op-amp helps to amplify input signals to give us a larger output. The resistors R5 and R6 of 10 kilo ohms each will form a voltage divider which supplies 4.5 volts, which can be derived from R5 divided by R5 plus R6 times 9 volts, which gives us 4.5 volts. And the capacitor C1 and C4 will block DC voltage from the input while allowing AC signals to pass through onto the next stage. To start on stage 1, I connect my power supply to VCC and ground, and my function generator to the positive terminal of capacitor 1. And then I connect my oscilloscope probe channel 1 to test point 1 and oscilloscope probe channel 2 to test point 2. Then over here, I made sure that the power supply is supplying 9 volts to the circuit. Next, I set the function generator to sine wave and the frequency of 1000 kHz and 200 mVPP. And as you can see, at 1000 kHz, we can observe a sine wave with an approximate value of 3.36 volts. Over here, I am changing from DC to AC coupling as we are measuring AC signals. And after changing, I ensure that I can see both sine waves clearly by adjusting the oscilloscope channel 1 and 2 respectively. It is calculated that the maximum voltage gain is 23 and it can be derived from 1 plus R2 over R3, which is equals to 1 plus 220 kilo ohms over 10 kilo ohms, which gives us 23. However, from what I have measured, the actual voltage gain is 3.36 volts over 280 MV, which gives us 12. From the table of values that I've recorded from the measurement, you can see that as the frequency increases, the gain also increases until it reaches the maximum gain, which is 22.5, which is also equivalent to 28.1 decibels. So, based on the frequency response curve, the low frequency will be at 16 Hz while the high frequency will be at 1200 Hz. Therefore, the bandwidth will be 1.2 kHz minus 16, which is equals to 1184 Hz. Now for stage 2, which is the closed loop inverting amplifier, we will test for the input at TP2 and output at TP3. Stage 2 shares the same IC as stage 1, the ICTL072. It is a closed loop negative feedback inverting amplifier, and it consists of a negative feedback loop and resistors R9 and R10 of 10 kilo ohms each, which form a voltage divider that supplies a DC voltage of 4.5 volts. For the closed loop voltage gain, it can be found using the formula negative RF over RI, or also V out over V in. So to find V out, we can use V in times negative RF over RI. Over here, I am shifting my oscilloscope probes from TP2 to TP3 and TP1 to TP2 respectively. For stage 2, we should observe an inverted output waveform to be generated, and as we turn the trimmer, the waveform should become saturated or cut off. These are the results I've gotten from stage 2. Moving on to stage 3, the active filter stage. It is where the input will be at TP3 and output at TP4. It is a Sallen-Key second order low pass filter, which consists of two low pass RC networks of resistors R7, R8 and capacitors C6 and C7. The low pass filter, which only allows low frequencies to pass through while rejecting all the high frequencies. Resistors R11 and R12 form a voltage divider which supplies an AC voltage of 4.5. By placing channel 1's probe of the oscilloscope to TP3 and the channel 2's probe of the oscilloscope to TP4, we would be able to get a filtered output voltage of 4 volts, and the output waveform at test point 4 will be determined by the output at test point 3. Hence, by adjusting the trimmer at stage 2, it can also adjust the output at stage point 4. So this is the result for my stage 3, where my channel 1's voltage is 7 volts and my channel 2 voltage is 4.06 volts. From the table of values that I've recorded from the measurement, you can see that as the frequency increases, the gain would also increase until it will reach the maximum gain of 0.99. So based on the frequency response curve, the minus 3 decibel line would be at 0 minus 3 equals to negative 3 decibel, and the high frequency would be at 1200 Hz. Hence, the bandwidth will be equals to 1200 minus 0 equals to 1200. Now finally moving on to stage 4, which is the audio amplifier stage, where the input will be at TP4 and output at TP5. It is a audio amplifier that drives the speaker. Capacitor C13 blocks DC voltage, which allows AC signals to pass through to reach the speaker, whereas capacitor C15 increases the R17 bypass high frequency to remove noise, and there is no voltage divider at this stage. To test for stage 4, we will place channel 1's probe of the oscilloscope to TP4 and channels 2 probe of the oscilloscope to TP5. By doing this, we should be able to get an output voltage of around 4.06 volts. By adjusting the trimmer P2, we can control the output at test point 5, and the final output will be the maximum sine wave without being saturated.